Piecewise defined functions are so named because they have algebraic expressions that define pieces of the function depending on where you are in its domain. And here we have f of x is equal to 3 minus 1/2 x. And that rule applies when x is less than 2. 2x minus 5 is the rule that applies when x is greater than or equal to 2. Let's graph the pieces of this function as though it wasn't a single function. So we'll graph 3 minus 1/2 x, or y equals 3 minus 1/2 x, and then y equals 2x minus 5 separately, and then we'll see what's going on with the piecewise definition. Well, I have my set of axes, and to graph y equals 3 minus 1/2 x, I'm first going to plot the point at the y-intercept of 0, 3, and then use the slope to count down 1 and over 2, down 1 and over 2. Connect those points with the line, and there is y equals 3 minus 1/2 x. Likewise, for y equals 2x minus 5, I'm going to plot a point on the y-axis where y is negative 5, and then using the slope, up 1 and over 2. Connect those points and I get another line. This is obviously not a function because it fails the vertical line test. Remember, the graph of a function needs to pass the vertical line test. That is, any vertical line can pass the graph of a function at most one time. So now we bring in the fact that these definitions were intended only as for pieces of the graph. That is, the blue line, y equals 3 minus 1/2 x, is only supposed to apply when x is less than 2. So if we look at the x-axis, if I go up to x equals 2 and shade to the left, that's the part where x is less than 2. Only in that region should I have blue graph. So let's get rid of the blue graph that's to the left of this point here. And then this was strictly less than, x is less than 2. We'll get into that a little bit more in just a second, but that means that I need to take this closed dot, and turn it into an open circle. Now the other line, y equals 2x minus 5, is supposed to apply when x is greater than or equal to 2, and so on our x-axis, I'm going to start it at 2 and then shade to the right. And it's only on this region that I should have the green graph. So I'll erase everything to the left of 2 for the green curve. And now I have this graph that's got a blue piece to the left of 2 and a green piece to the right of 2. And then I'm going to emphasize that at the leftmost endpoint of the green graph, I should have a closed dot because of that, or equal to. Now, when you see the definition of a piecewise defined function, you won't see both of them being non-strict inequalities. That is to say, I'm not going to see x is less than or equal to 2 here and x is greater than or equal to 2 for the other definition, because then I run the risk of failing the vertical line test. Now let me get rid of all the extra stuff here. And I'm going to label the x-axis right there at 2. I don't need to label every single hash mark. What I've done is I've indicated my scale in both the x and y directions. And this is the graph of our function. It's in 2 pieces. It's piecewise defined. As far as the domain, the instructions were sketch the graph and give its domain. Sometimes in a situation like this, people will say, oh, well, x goes from negative infinity to 2. Don't include 2 because this doesn't say to include 2, right? The x is less than 2. And then from 2 to infinity. Well, this says go from infinity to infinity, and then don't include 2, and then do include 2. This is not how we express the domain of a piecewise defined function. No matter what real number I'm thinking of, if it's less than 2, I have a rule for it. If it's greater than or equal to 2, I have a rule for it. The domain is all real numbers. So when you think of a piecewise defined function, it's got a single domain, and in this case, it's all real numbers. Now let's consider a function that you should be familiar with, the absolute value function. Let's look at its graph. As you probably know, the graph of the absolute value function looks like a V. Now, to the right of the y-axis, it looks like y equals x, right? The output matches the input. To the left of the y-axis, it looks like y equals negative x. If I put a negative input into the absolute value function, it will spit out the positive version of that number. So we can actually express the absolute value as a piecewise defined function. The absolute value of x is equal to x if x is greater than or equal to 0, and it's equal to negative x if x is less than 0. Being able to express an absolute value function as a piecewise defined function is important because, as you'll see throughout this course, we can't perform calculus on absolute value expressions. We will always need to split them up as a piecewise defined function. And I'll make a point here to say that the point at which the definition switches, in this case 0, corresponds to the vertex of the absolute value graph. So if we were looking at the absolute value of, g of x equals the absolute value of x minus 2, that's a shift to the right of 2 units. And so we would express the absolute value of x minus 2 as being equal to x minus 2 as long as x is greater than or equal to 2. And then it's the negative of x minus 2 as long as x is less than 2. So again, the point at which the domain is split is associated with the x-coordinate of the vertex of the graph.